What is up, young chemist? Mr. Rosen here. How's it going? Hope you're doing well. The topic of this video is electromagnetic radiation and wave calculations. So we're going to talk about what electromagnetic radiation is, the electromagnetic spectrum, the different sections of the electromagnetic spectrum. We're going to talk about concepts like wavelength, frequency, and wave speed. We'll do calculations with those. We'll also consider the energy of the photons. So the first part of this video is going to be defining some terms and explaining some concepts. Of course, at any point during the video, you're welcome to pause it and just kind of read what's on the screen, and you can always, replay stuff. So, electromagnetic radiation is energy coming from the sun. In our case, although other stars will produce electromagnetic radiation as well. The electromagnetic radiation, we often refer to it as light. Some of that electromagnetic radiation we can perceive with our eyeballs, visible light. But a lot of the electromagnetic radiation we cannot see with our eyes, but maybe we feel or experience or use technology in order to detect or utilize that electromagnetic radiation. So we'll talk more about that. But electromagnetic radiation travels at the speed of light in a vacuum. Okay, a vacuum means empty space. And that's pretty close to 3 times 10 to the 8 meters per second. 2.998 times 10 to the 8 meters per second. We'll use that for our speed of light. So in terms of types of electromagnetic radiation, we'll see in a minute, you could have visible light, you could have X-rays, you could have radio waves. Those are all electromagnetic radiation, and they all travel at the same speed, the speed of light, which is a constant in a vacuum. The speed of light will differ if the light is traveling through a gas or a liquid or a solid. When we're talking about electromagnetic radiation, okay, it displays wave-like behavior. The term wavelength is the distance between 2 consecutive peaks or troughs on a wave. And really it's just 2 consecutive 2 points on the wave that are the same. So, if you were going from right here, this is a peak, to the next peak, this would be one wavelength. Okay? And wavelength is represented using the Greek letter lambda, which looks like this. So this is one wavelength. And you could literally measure that. This is maybe about an inch wavelength. Now you could also measure from here to here, and you would find that this is also the same length, one wavelength. So this would be measuring between 2 troughs. But if you measured right here and right here, that would also be one wavelength. It's one cycle through the wave. The other concept that we're going to talk about is frequency. Okay, now frequency indicates how many waves pass a point per unit time. Usually it's frequency in terms of per second, and that's what hertz is. Hertz is a unit of frequency, which is cycles per second. Greek letter for that is nu, which sort of looks like a V, but that's what that is. So if I were to just sit at one point and count the waves as they moved past me, 1 wave, 2 waves, 3 waves, 4 waves, how many waves go by per second, that would be my frequency in hertz. And it's usually a pretty big number. Maybe like for visible light, it's maybe 10 to the 14 waves per second. So here's the equation which we'll be using. Wave speed is wavelength times frequency. Now, speed, you you could think about it in terms of like meters per second, distance per unit time, right? This wavelength is probably going to be in meters, and this frequency tells you how many waves go by per unit time. So when you multiply these two things, you're going to end up getting a rate, speed. So this is what just says wave speed. This is for any wave. So if you're looking at a wave in the ocean, let's say, okay, a wave made where the liquid water is the medium that the energy is traveling through, this holds true. Okay, for electromagnetic radiation, the wave speed is the speed of light, which is 2.998 times 10 to the 8 meters per second, because all electromagnetic radiation travels at the speed of light. So if it is electromagnetic radiation, this is the wave speed, the speed of light. If it's not electromagnetic radiation, but displays wave-like behavior, then you don't know what the wave speed is. You have to calculate it based on the wavelength and the frequency, right? A wave in water, a sound wave, these things have wave-like behavior, but we have to calculate the speed. Now, wave has electromagnetic radiation. We say it displays wave-like properties, but it also has properties consistent with a particle. This is called the wave-particle duality of light. So you could think about light as a stream of tiny packets called photons. Okay, photon is sort of like a tiny packet of electromagnetic radiation. And the properties of the electromagnetic radiation are related to the energy of the photons making up that radiation. So a higher energy photon or higher energy photons will give you a light sample that will have a shorter wavelength and a higher frequency. Lower energy photons will give you a longer wavelength and a lower frequency. So here at the bottom, I have an electromagnetic spectrum. Okay, this is printed in black and white, which is not very helpful, but this would be like violet. That's supposed to be a V, sorry. Violet, and this would be red. So this is supposed to be like a rainbow. Okay, so maybe this is about green, this is about yellow, this is about orange, this is about blue. So this is the rainbow. So the visible light section of the spectrum is just this little section here. Okay, and you can see the wavelength. So as we're over here, you have longer wavelengths. So our eyeballs can only perceive a certain range of wavelengths, usually between maybe about 400 nanometers to about 700 nanometers ish. And if something has a longer wavelength than that, we won't be able to see it with our eyes, but you could feel it. It'd feel maybe like warmth on your skin, and we can use infrared cameras to detect that electromagnetic radiation. The longer wavelength still is microwaves. Microwaves are used, like literally in a microwave to cook food, but also with cell phone signals, TV signals, and sometimes you can see a category of TV in here, but microwave is fine. And then we have radio waves, which are even longer. And you can see some of the wavelengths on this. This ranges from 1 meter per wave to 1,000 meters for one wave. So radio waves have long wavelengths. And you could even break this down into FM and AM. FM would be a little shorter, AM would be a little bit longer. Now I also want you to recognize where you have a long wavelength, you have a low frequency. Where you have a short wavelength is where you have a high frequency. And also notice energy increases as you move to the right. So, as the energy of the photons and the electromagnetic radiation increases, the wavelength gets shorter and shorter, and the frequency increases. So, if something has a shorter wavelength than what we can see with our eyes, it's going to have a higher energy, and it's going to have a higher frequency. So, violet, right, is the highest energy visible light we can see. If something has more energy than that, it's called ultraviolet. And we can't see that with our eyes, but we might experience it. If you spend too long in the sun, maybe you get a sunburn. That is from UV, damaging UV rays, ultraviolet rays. And anything that has more energy than visible light has potential to be damaging to us as organisms. So ultraviolet light can be damaging. We want to limit exposure. X-rays, you want to limit exposure. These are even higher energy, shorter wavelength, higher frequency X-rays. When you go to get an X-ray done at the doctor, they put a lead vest over your chest. That's to minimize exposure of your vital organs to this potentially damaging radiation. And even higher energy than that is gamma rays. We mentioned them earlier when we were talking about nuclear chemistry. It's very high energy radiation will just sort of zoom right through you, but could disrupt electrons and is what's called ionizing radiation, which is potentially damaging to bonds. And if bonds are being broken by radiation, you can get some mutations and abnormalities and cancerous cell growth. Anyhow, this is the electromagnetic spectrum. It's really important to know longer wavelength means lower energy, lower frequency. So these things down here, like microwaves and radio waves, we're not too worried about these, right? We use radios all the time. Let's use microwaves all the time. People don't seem to be dropping dead because of those. At least, that's what studies have shown. And it's because they're such low energy, they don't have potential to damage cells and break bonds. Whereas some of this higher energy radiation, we know what happens when you're exposed to that, and it's bad. So we try to limit our exposure. High energy means short wavelength, high frequency. Low energy means long wavelength, low frequency. Let's do some calculations. So, if you would like to, you can pause the video and try to solve these problems. Most of them are related to electromagnetic radiation, but I think at least one is a wave which is not electromagnetic radiation. So, solve the problems, and I'm going to go over them in just a minute. Okay. The first problem says the speed of light is approximately 2.99 times 10 to the 8 meters per second. What is the frequency of a microwave or microwaves with a wavelength of 0.2 meters? So, the speed of light, 2.998 times 10 to the 8 meters per second, the speed of light equals wavelength, which is 0.0200 meters, times frequency, right? As we learned just a minute ago, the speed of light is equal to wavelength times frequency. We know the speed of light. We know the wavelength. What we don't know is the frequency. And the frequency is symbolized using the Greek letter nu. So you could think about that as x, even though it looks like a v. we're solving for frequency. So if you want to get that all by itself on one side of the equal sign, divide by 0.02. This will cancel. Whatever you do to one side, you do to the other. So this is getting divided by 0.0200, and this is meters. On our calculator here, hopefully you can see that. The lighting's a little weird, but 2.998 times 10 to the 8th. That number is going to be divided by 0.02. And the calculator says, sorry if it's a little hard to read, it says 1.499. Okay, now this number has two sig figs, so we'll say 1.50. And then it says E10. So that means times 10 to the 10th. Now, this is the speed of light, and this is our wavelength. If you take meters per second and you divide by meters, you're left with 1/seconds, what are called inverse seconds, which is the same as hertz, which is a unit of frequency. Okay, so if you wrote hertz or you wrote 1/seconds, another way to write 1/seconds would be s to the -1. These are all fine, but you need to be comfortable with each of them. Okay, so let's try this next one. It says, the string on a piano that produces an A sharp vibrates with the frequency of 235 hertz. If the sound waves produced by this string have a wavelength in air of 1.46 meters, what is the speed of sound? What is the speed of sound in air? Okay, so this problem, it's not electromagnetic radiation. It is a sound wave. So we don't know. They're asking us for the wave speed. Okay, so they're asking us for the wave speed. The wave speed is going to equal the wavelength times frequency. They give us the wavelength, 1.46 meters, and they give us the frequency, which is 235 hertz. Okay, now, again, just for our sake of units, hertz is inverse seconds, 1/seconds. So if we take, all right, I'm going to take the calculator here, 1.46 wavelength times frequency, 235, we get, going to round to 3 sig figs, wave speed equals about 343. And now what's our unit? Meters per second, because we're multiplying these two. And that is, very close to the speed of sound, which is like 1,130 feet per second. And there are, well, we'll just leave it at that. That's what the answer should be. It's fine. Makes sense. Okay, next one. Green light. Okay, so this means it's visible light and it has a green color. So that means it's electromagnetic radiation. They tell you the wavelength. If you wanted to count this up, this is 5.1 times 10 to the -7 meters. Okay, you can count 1, 2, 3, 4, 5, 6, 7. So that's our wavelength. It says the speed of light is, again, we know that, the speed of light 2.998 times 10 to the 8, that's meters per second. Sorry, my handwriting's never very good. And then it asks you calculate the frequency. So this is actually just like problem number 1. We're solving for frequency. So that's like x. You want to get it all by itself on one side. So 5.1 times 10 to the -7 meters. That will cancel this. 5.1, do that twice, times 10 to the negative 7 meters. Again, our unit is going to come out as hertz, which is 1 over seconds. And let's see how it goes. So 2.998 times 10 to the 8, that is our speed of light. And it's going to get divided by, I'll just put it in scientific notation, 5.1 times 10 to the negative 7. All right, and then what we get is to 3 sig figs, 5.88 times 10 to the 14th hertz, or inverse seconds. That's our frequency. Next one, okay, solving for a different variable. Calculate the wavelength of electromagnetic radiation. So we know it's electromagnetic radiation. That means we know the wave speed, right? The wave speed is 2.998 times 10 to the 8 meters per second, because all electromagnetic radiation has the same speed. And that equals wavelength, which is Greek letter lambda, times frequency, which is 8.5 times 10 to the 14th hertz. Just like before, we're solving for this, like it's x. So we're going to divide by 8.5 times 10 to the 14th. That cancels. Whatever you do to one side, you do to the other. 8.5 times 10 to the 14th hertz, which is the same as 1 over seconds. And what you'll get is your wavelength. Wavelength equals, let's see, maybe this is a little bit easier to see up here, 2.998 times 10 to the 8th. So that's our speed of light. It's going to get divided by 8.5 times 10 to the 14th. Okay, so the speed of light is getting divided by our frequency. If you do that, you get an answer. And now your answer is going to come out in just a length in meters. So to actually only 2 sig figs on this, it's going to be 3.5 times 10 to the negative 7 meters. Okay. And if you wanted to convert that, that's about 350 nanometers, which is a pretty common unit to use. This is just outside of the visible section, just shorter than the visible section. And so this light is going to be, based on the wavelength, this light's going to be in the ultraviolet section. Okay, probably just beyond here. And that will be, that would be the type, it would be ultraviolet. All right, we'll just leave it at that. So far we've talked about concepts of wavelength, frequency, and wave speed. We've done calculations. We talked about the electromagnetic spectrum and types of radiation. One other thing that we need to talk about is the energy of the photons in this electromagnetic radiation. So we figured out how to relate wavelength and frequency to the wave speed. How is that connected to the energy of the photons? So scientist and mathematician Max Planck and Albert Einstein, brilliant, both of them brilliant minds. In the late 1800s, early 1900s, were doing work with physics, and both kind of came to the same relationship around the same time. And so this is often referred to, this is the more typical form that you see, but this is equal to or the same as this. Okay, but this is known as the Planck-Einstein constant. Sometimes you hear people pronounce it Planck, which is probably more appropriate, but I'm just not that cool. So anyhow, the E stands for energy. The unit of energy is joules. We'll learn more about that later in the year. H is what's called Planck's constant, and it's a really small number. 6.626 times 10 to the negative 34 joules seconds. And C is the speed of light, so this is giving it a letter now, right? You've probably heard E equals mc squared, where the C is the speed of light, and there E is energy too. Lambda is wavelength in meters, and nu is frequency in hertz or inverse seconds. So the energy of the photons in the electromagnetic radiation is equal to Planck's constant times the frequency. And Planck's constant is, like the smallest packet of energy that the photon could have, and it's just going to have some multiple of this, which is a very novel concept at the time. The reason that these are the same is if you remember from the problem above, here is frequency. If you take the speed of light divided by wavelength, you get the frequency, right? That's exactly what we did in these problems up here, right? I took the speed of light and divided by the wavelength, and I got the frequency. So taking c, which is the speed of light, and dividing it by wavelength, that right there, c divided by wavelength, that is the same as frequency. And that's why these are the same thing. So depending on what information's given, if you know wavelength, you might just plug this one in. If you have frequency, you might just plug this one in. But be comfortable with both. And yes, you should know Planck's constant and the speed of light, although our periodic table will probably have both of these values written on the back of it. It's useful to just know them. You do a bunch of practice problems, eventually you will kind of internalize it. So let's do some practice problems with energy, wavelength, and frequency. All right, okay. So here are 3 of the problems. I guess I want you to be able to read them all, so that way you can read them all, although it's at the bottom. If you would like to pause to try to solve these problems, go ahead and do so. We will go over the answers in just a minute. You can pause the video if you need to. Okay. So this problem, number 1, it says find the energy in joules per photon of a microwave radiation with a frequency of this. Okay, so what do we know? What are we solving for? We need to solve for E, which is our energy value. And we are given frequency. Now, the equation, the handy-dandy equation, is E equals H nu, right? E equals Planck's constant times frequency. We're solving for this. Planck's constant is a constant. It's the same number every time. So E equals H, Planck's constant, which is 6.626 times 10 to the negative 34 joule seconds. And then frequency, 5.91 times 10 to the 10th hertz, which is the same as 1 over seconds. Now we just multiply them, okay? If we do multiply them, you'll see that seconds is going to cancel, and we will get our answer in joules, which is typical for an energy problem. So let's plug some numbers in here. 6.626 times 10 to the negative 34. Okay, this is Planck's constant. It's going to get multiplied by 5.91 2.91 times 10 to the 10th. And we get a small number, because this is joules per photon. Photon's tiny. So to go to 3 sig figs here, we go 3.92 times 10 to the negative 23 joules. And that's a per photon value. So pretty straightforward. Now, the next problem, I'm going to zoom in a little bit here. Hopefully that's helpful. The next problem says a sodium vapor lamp emits light with photons in the wavelength of, okay, so this is sort of 570 nanometers, kind of a yellowish color light that's emitted from a lamp. What is the energy of these photons? So in this problem, we're solving for E again, but we don't have the frequency like we did above. We have wavelength. Now, you could use the wavelength and the speed of light to solve for frequency, right? Or you could just kind of do it all at once and plug them into E equals hc over wavelength, right? You could take the speed of light and divide it by this number to get frequency and then multiply it by h like we did above, or you can just plug them all in here, okay? Which I'll just do for the sake of writing it out. So E equals h, which is Planck's constant, 6.626, okay, 6.626, sorry if that's a little ugly, times 10 to the negative 34 joule seconds. So this is our Planck's constant. And then we're going to have C, I'm going to run out of space, 2.998 times 10 to the 8 meters per second. So H and C, Planck's constant, the speed of light. And that's going to get divided by the wavelength, which is given here, 5.79 times 10 to the negative 7 meters. Okay, now in terms of our units, meters divided by meters will cancel, seconds times inverse seconds will cancel, and again, E will give you a value in joules, which is a unit of energy. So let's see what we get. Now, this could get a little complicated in your calculator. 6.626 times 10 to the negative 34. So that's our Planck's constant. And I'm going to say times, now I'm going to open my parentheses, 2.998 times 10 to the 8th, close parentheses. So that's taking Planck's constant times the speed of light. I'm going to hit enter. Okay, so that number is the product of the speed of light and Planck's constant. Now that is going to get divided by, I'm going to open parentheses, 5.79 times 10 to the negative 7, close parentheses. So the product of these two numbers is going to get divided by our wavelength. Paying attention to parentheses is very important here. And the value I get going to 3 sig figs is 3.43 times 10 to the negative 19 joules. And that's joules per photon. Okay, we continue along. Now, each one of these is meant to be a little bit different. So in the first problem, we are solving for E when we had frequency. The second problem, we are solving for E when we had wavelength. In this problem, they actually give you E, right? Look, they give you E. So, and you're solving for frequency. So E equals H frequency. And they give us E. So that means 2.29 times 10 to the negative 18 joules equals H, which is Planck's constant, 6.626 times 10 to the negative 34 joule seconds times frequency. This is our Greek letter nu. Which kind of looks like a V. So that's what we're solving for. It's like solving for x, right? I'm going to divide by 6.626 times 10 to the negative 34 joule seconds. That will cancel. Whatever I do to one side, I do to the other. So 6.626 times 10 to the negative 34 joule seconds. And here, you can see joules divided by joules will cancel, and we'll be left with inverse seconds, which is the same as hertz, which is the unit of frequency, which is what we're solving for. So let's do this. 2.29 times 10 to the negative 18. Okay, so that's our energy per photon. It's going to get divided by Planck's constant, 6.626 times 10 to the negative 34. And what we get is going to 3 sig figs, 3.46. 3.46 times 10 to the 15. And that's hertz or inverse seconds. That is our unit of frequency. All right, so that was a little different, solving for frequency when energy was given. And now let's do one that's even more complicated. Okay, this is meant to be sort of a challenge problem here, a little bit of a challenge problem. 4. A ruby laser, so light, which is sort of narrowed into a particular wavelength of 700 nanometers. Calculate its energy in joules. This should be a capital J. Okay. So one thing to note here is this wavelength's given in nanometers. And if we're looking at our other constants, the speed of light is in meters per second, right? And if we're going to be using that, we need to have our wavelength in meters. So we need to convert 700 nanometers into meters. Now, you might need to go back and review our metric prefixes, but it says there are 1 billion nanometers in a meter. So 1 meter is 1 billion nanometers, and that's a 1 with 9 zeros after it. So if we do this, nanometers will cancel, and you'll be left with your answer in meters. Now 700 nanometers is 7 times 10 to the negative 7 meters. This is, like it says, red light. So anyhow, this is our conversion. So this is our wavelength. Okay, so that's the wavelength we're going to use. Okay, well, unfortunately, my document camera went out in the middle of making that video, so I just have to finish this last one here. Hopefully I can stitch the 2 video clips together, and apologize if there's a cut in the video. Anyhow, we converted 700 nanometers into meters. We did that by dividing by 1 billion, because that's how many nanometers are in 1 meter. And then we're ready to do what we did up here. Okay, we are going to solve for E when we know Planck's constant, 6.626 times 10 to the negative 34 joule seconds. And that's going to get multiplied by c, which is the speed of light, 2.998 times 10 to the 8 meters per second. And that's going to get divided by our wavelength in meters, which is 7.00 times 10 to the negative 7 meters. So we're going to plug all that into the calculator, and we'll write down what the calculator gives us. I want to put it up here so you can hopefully see what gets typed in. Okay, 6.626 times 10 to the negative 34. Okay, so that's Planck's constant. It gets multiplied by the speed of light. So open parentheses, 2.998 times 10 to the 8th, close parentheses. Okay, so this is the number you get when you multiply Planck's constant and the speed of light. And that'll be the same every time. And that's now going to get divided by our wavelength in meters, which is 7, put the zeros in there, they don't need to, but 7 times 10 to the negative 7, close parentheses. And we get our answer. Now in terms of our units, meters per second is getting divided by meters, so that cancels. And seconds times inverse seconds cancels, and you're left with, slide this up, E in joules, rounding to 3 sig figs, 2.84 times 10 to the negative 19 joules. That's the energy per photon value. That's a 19. Okay, so in this video, we learned about electromagnetic radiation, parts of the electromagnetic spectrum. We talked about wavelength, frequency, and wave speed. We did calculations with that. We also talked about energy of photons. We learned about Planck's constant and the Planck-Einstein equation. As always, you want to make sure that you're studying and practicing practice problems. The practice problems in this video are very, very, very similar to the practice problems in your lesson packets. So watch this video, pause it, rewatch it, use it to help you solve the problems in your packet. Good job. Hope you're doing well, staying healthy. Let me know if you have any questions or need anything. This is Mr. Rosen. Out.